Hello friends, welcome you all to my channel Civil Engineers. Today we'll continue with the second lecture in double integration method. As in the previous lecture we have taken cantilever beam, today also we'll proceed one more example in cantilever beam also, and the question is here: a cantilever beam loaded with uniformly distributed load throughout the span. Then we have to determine the maximum slope and maximum deflection. For now we'll proceed like this. First we will draw the picture of the given question, and it is like this. It has given a cantilever beam and it is loaded with uniformly distributed load throughout the span. And let us suppose span length is L. Okay, now since the beam given is cantilever, so no need of finding the reactions. Directly we can approach to find the mxx value. For that we have to cut the section, and cut the section in such a manner that it will includes load. See, let us take it is at a distance of x. If we are fixing A as a origin, then it will be at a distance of x from the origin, and the remaining distance will be L minus of x. And let us say this is W per meter. Right. Now we'll go to formulate the mxx equation. Before going there, let us understand the sign conventions. See, for if a given section, in a given section, whatever load is acting in the upward direction or to the left of the section or to the right of the section, we are taking it as a positive, right? And let us suppose a section, and if the load is acting in the downward direction, then for that we are considering the bending moment to be negative, right? Here we'll apply the same sign convention and we'll approach like this. mxx value will be since it is given W and it is acting at a length of L minus x, so see, it is our section and it is acting towards the right of the section and it is acting downwards, so we are taking it as a negative, and it is acting in a span of this, and since the given load is uniformly distributed, so it will again multiply by L minus of x divided by 2, because the net resultant of the uniformly distributed load will come at the center, so we are taking L minus of x divided by 2. So it will be minus of W divided by 2 into L minus of x whole square. As in the previous video also I have told to expand this part in order to reduce the error, so I am going to expand that, and it is L minus x whole square, means a minus b whole square, and it will be a square plus b square minus 2 times of L into x. Now we know that E into I d square y by dx square, that is equals to plus minus of mxx. Here I am taking mxx as negative, you can take it as a positive also, no issue. E into I d square y by d of x square, that is equals to W by 2 L square plus x square minus 2 into L into x. And let us now let us integrate it for the first time, and this will be our equation 1. If we are integrating equation for the first time, we will get E into I into dy by dx, and that will be equals to W by 2, we are integrating this part, L square into x plus x to the power of 3 divided by 3 minus x square divided by 2 will get cancelled, so directly I am writing L square into x plus c1. And let us suppose this is equation number 2, right? This is, I am taking it as equation number 2. Now I am integrating it for one more time E into I into y, that will be equals to w by 2 into L square x square by 2 plus x to the power of 4 divided by 4 3 are 12 minus x to the power of 3 divided by 3 into L plus C1 into x plus C2. Now my aim will be to find the value of C1 and C2. For that I will consider boundary. I will find the boundary conditions. Okay. For finding boundary conditions, let us take this figure as a reference. If I'm my origin, then it will be my 0 0. For this figure it will be 0 0, and total span of the beam is L. So here x will be L. So at this particular point, at point A, x is equals to 0, clear? Y is also 0 and dy by dx is equals to 0. Here x is equals to L, y will be maximum, right? And dy by dx, that will also be maximum. See, and the beam has tendency to bend in this manner, right? It will bend in this manner because at this point it is fixed, it is cantilever, so it is fixed at this particular point, so it has tendency to bend like this. Now now let us write the boundary condition. Our first boundary condition is x is equals to 0, y is equals to 0, and dy by dx is equals to 0. Second boundary condition is x is equals to L, y is equals to maximum, and dy by dx, that is also maximum. Now using equation number 1, equation number 2, I will find the value of C1. C, E into I dy by dx, that is equals to w by 2 L square into x plus plus x to the power of 3 divided by 3 minus x cube into L plus of C1. Here I will put this part, here I am putting dy by dx is equals to 0, so it will be 0, right? Here I am putting x is equals to 0, so this part will be 0, this is also 0, x is equals to 0, here also this is also 0, so I am getting C1 is equals to 0. Similarly, by using equation 3, okay, I will find the value of C2, and like this, C, E into I into y, that will be equals to w by 2 into L square x square divided by 2 plus x to the power of 4 divided by 12 minus x to the power of 3 divided by 3 into L. No need of writing C1 part, that because C1 is equals to 0, okay, plus of C2. C, I will use boundary condition, these boundary conditions, x is equals to 0 I will put, and y is equals to 0 I will put, so this part will become 0, this part become 0, this part will also become 0, this part will also become 0, so I am getting the value of C to be 0. Now I got the value of C1 and C2. I will put it in the equation 1, equation 2 and equation 3, and equation 2 and equation 3 becomes like this. See, so E into I into dy by dx, okay, that will be equals to w by 2 into L square into x plus x to the power of 3 divided by 3 minus x to the power of 3 into L plus C1, no need of writing C1. Now I have to find maximum. Sorry, this is not a cube, this is square, I'm sorry. Here also it will be square, sorry for that. Now this equation is also known as slope equation. This is also known as slope equation. Now I have to find maximum slope, and slope will be maximum at x is equals to L, because at this point it is fixed, so it will be 0, as I have already discussed. So maximum slope will be at x is equals to L, so I will put x is equals to L. So E into I dy by dx, and it will be maximum at x is equals to L, putting x is equals to L. Okay, so w by 2 into L square into L plus L to the power of 3 divided by 3 minus L to the power of 3, that's all. And once you solve this, you will get w into L to the power of 3 divided by 6 times of E into I dy by dx maximum. Now by putting value of C1 and C2 at equation number 3, I will get a deflection equation, and it is like this: E into I into Y, that will be equals to w by 2 into L square x square divided by 2 plus x to the power of 4 divided by 12 minus x to the power of 3 L divided by 3. No need of writing C1 and C2 value. Okay, this is also known as deflection equation. Now I have to find maximum deflection, and deflection will be maximum at x is equals to L only, because at this particular point this is fixed, so it will be 0, no deflection will be there. Okay, so I am putting here x is equals to L. X is equals to L, I am putting in this equation. I will get E into I into Y, that will be equals to w by 2 here L to the power 4 divided by 2 plus L to the power 4 divided by 12 minus L to the power 4 divided by 3. Once you solve this, you will get y maximum as that is equals to w into L to the power of 4 divided by 8 times of EI. So this is our maximum deflection. Thank you friend for watching my video. If you like the video, then please subscribe it, like it, and put comment if any improvement is to be done. Thank you for watching my video. Thank you friends.